Flashing across the California desert skies, the airplanes you see here are writing new chapters in the story of man-made flight. There she goes.
This is my first opportunity to greet you as Deputy Administrator of the National Aeronautics and Space Administration. Together, you and I must make our new agency a most unusual place. An organization that can challenge conventional wisdom.
We can engineer anything, we can write the requirements for it.
We're going to make your idea work. This particular idea is quite disruptive.
A typical flight, of course, starts under the wing of the B-52 mothership.
This sleek, high-speed machine would have made Rube Goldberg proud.
The manner in which we fly re-entry from space on the space shuttle was pioneered on the X-15.
X-31 pretty much wrote the book on thrust spectrum, along with its sister program, the F-18.
An observation or an occultation is one of the more challenging missions that Soviet people.
Right now, we are looking at the dawn of a new era of aviation.
Something has now emerged that might make even our most elegant theories workable.
Scientists developed equipment which would be able to think.
Machines that do things and make choices without human beings. That uncanny spectacle is automation.
Capable of storing, processing.
Calculations that would ordinarily take hundreds of man-hours. Unique ability to check itself on possible errors.
Cheaper and quicker and better.
Electric eye, lemon switching, servo mechanism.
Secretary, librarian, banker, teacher, medical technician, bridge partner.
Billions of changing data into a continuous flow of interpretation. Aladdin's lamp couldn't do more.
Joy, rolling machine, electric drill, it's all automation.
Computers have taken wing.
By the late 1960s, digital computers had become more available.
Using data about the aircraft's performance, the computers vote on the correct amount of control deflection to make in response to the pilot's stick and rudder movements.
This system could make air travel of the future smoother and safer by reducing aircraft vibration through automatic response from the computers to the aircraft controls.
We did the digital engine control. We had a thoroughly large digital computer that ran the engine and the inlet and exhaust system. We did an integrated control study to provide digital control of the inlet, autopilot, throttle, data, and navigation system. A digital computer here, a major improvement in the capability of the airplane.
Test pilots are flying a plane without having to leave the ground. It's a new way of flight testing advanced aircraft that's both more economical and less hazardous. A research pilot in a realistically recreated cockpit on the ground, complete with flight controls, flies the remotely piloted craft using computers and television.
The airplane includes computers. Those computers take stick command and
continuously monitor what the airplane is doing and compares it to what the pilot wants the airplane to do.
The computers signals the control surfaces to not only execute the pilot's maneuver, but also to counter any attempt by the X-29 to veer out of control.
Artificial intelligence area, and it's called aircraft automation. The technologies that end up coming out of this would be autonomous flight vehicle technology.
ERAS stands for Environmental Research Aircraft and Sensor Technology. Platforms that could fly higher and longer than the current piloted airplanes, do science missions and other commercial applications.
Primarily the dull, dirty, and dangerous.
We can go all the way up to where the airplane can fly itself completely autonomously with no input from anyone on the ground.
Fly up to 50, 60,000 feet, fly a circle loop perhaps over a city, providing the capability that a satellite now does.
Now that we can fly for on the order of 8 to 10 to 12 hours, we can look at long duration processes, biogeochemical cycling, looking at carbon and nitrogen moving through an ecosystem.
To sort of kickstart a commercial UAV industry.
The technology that we've seen here in this test is what would be the foundation for a follow-on program to really address the issue of how can UAVs routinely operate in the national airspace system.
The primary benefit of this technology is the ability of it to adapt to the unknown, whether it be a system failure, battle damage, icing on the wing, or flying in an unknown atmospheric environment.
The aircraft may be able to be flown, but the pilot may or may not be able to find a solution to how to fly that aircraft.
Neural net control systems where the controls are going to teach themselves and keep getting smarter from flight to flight.
It can reconfigure the airplane in an optimal way in order to give you the best flying qualities.
Okay.
There is no operator of the vehicle itself on the ground. Basically, the role that the human plays is more in managing the mission, an orchestra director, not the instrument player.
The vehicle will complete all the autonomous actions necessary to release the weapon optimally positioned to hit the target.
One of the next things that we'll be demonstrating in UCAV is the collaboration amongst aircraft. How do sets of aircraft interact together in almost a social form?
We're going to examine the feasibility and technical utility of actually being able to fly two airplanes or multiple aircraft in formation with each other.
Now the trick to this is to make sure that they fly in formation close enough that they can extract the advantage without obviously running into each other.
The station keeping would be fairly close proximity for hours. The workload on the flight crew would be quite high, so we started to develop autonomous algorithms to do the station keeping. So you basically would have an autopilot that you could engage.
The computers are flying the airplane without your stick input, even in the system, to allow a piloted airplane to take 2, 3, or 4 unpiloted vehicles on a long distance trip.
We're just getting started on this technology. We'll use this technology to refuel unoccupied combat air vehicles.
The basket's slightly moving. Looks like it's going high. Okay, it detected a miss and came back on its own, so I did not do anything. She's got it. She's got it. Congratulations, guys. That was fantastic.
The Autonomous Soaring Project has one simple goal, is to program a small UAV to soar in thermals, similar to the way a glider pilot or birds do. It has been reprogrammed to automatically detect that it's in an updraft and then use that updraft by circling. There's a wide variety of applications for this technology to help UAVs do things like forest fire detection, police surveillance, border patrol, and weather monitoring.
If the aircraft was damaged, you don't have to necessarily just rely on the pilot to compensate and fly the airplane. Adaptive flight controls, autonomous flight controls, different things where we're using the airplane to assist the pilot.
It'll take over basically the controls of the airplane as far as flight stability.
The platform precision autopilot is capable of staying on a given path within about 15 feet. It allows the synthetic aperture radar system to fly over essentially the same path more than once. This obviously has some potential applicability when you're looking at Earth's surface movements, such as after an earthquake, or if you're looking at ice pack melting.
For the F-16, we went out and tested the system and based them on actual mishap cases. It prevented every single mishap. What we're developing here is merely an aid should the pilot get distracted or disoriented. By automating it, we can take out the pilot reaction time entirely.
The computer takes full control away from the pilot for a very brief period of time, and it redirects the trajectory of the aircraft to save the human.
ADS-B is automatic dependent surveillance broadcast. It's equipment on board an airplane that transmits its position and velocity information twice per second.
We were really trying to prove that we could use ADS-B as a way to do coordinated flight between multiple vehicles.
This system is present on a lot of manned aircraft, but we were one of the first UAS to perform testing of it in the national airspace. NASA has a project for integrating UAS.
So one day, UAS could hopefully fly with other commercial airlines and everybody will fly together safely.
There's various benefits to integrating unmanned aircraft, being able to monitor specific weather systems, monitor fires, delivering packages to your doorstep.
Operations to deliver medical emergency supplies, infrastructure, surveillance, and monitoring.
The technical side is a big challenge, but being able to integrate them safely
is maybe even a bigger challenge.
To have thousands of these vehicles flying at the same time, you're going to have a lot more automation on the vehicle and in the airspace system.
Regulations for operations of the vehicle, regulations for airspace, regulations for infrastructure.
These aircraft are going to be highly autonomous, piloted, optionally piloted, unpiloted vehicle.
It's not just looking at the UAM, it's actually integrating the small UAS, the package delivery, or even the larger cargo delivery.
Subscale aircraft, we use those for a variety of reasons, to test things like new technology, which could be hardware or software, or even a completely new vehicle. You can do almost anything you want without much risk. And you can realize those gains very quickly. We're researching some level of autonomy. The aircraft, in most cases, are capable of taking off, flying around, and landing without any human intervention. Things like ardupilots and multi-rotors and flying computers are allowing kids to play with research type tools that they never had access to before. So it's sort of driving in this new robotic learning type environment that never did exist.